Therefore, to develop the matrix equations or elements of matrix, we are going to use different methods. So one of the method is called conjugate beam method. Of course, I think you have not come across this particular chapter in your essay 1. So we need to just revise what is conjugate beam and what it is going to give you. See, in structures, for an engineer, the important things are first one is load. So, external loads are going to act on a structure due to various things. Say, for example, if you take beam, it has got its self weight, then moving load on that particular structure, and hence load calculation or load consideration becomes an important part of an engineer. Then, secondly, you are analyzing the beam. Once load is known to you, you are going to determine shear force. See, why we need to determine this shear force? Because one of the mode of failure of any structure, you take column, beam, or a frame, or any structure you take, the first mode of failure may happen in the form of shear force. So, to make the structure resistive against this particular shear force, we must calculate the shear force. Already in your strength of materials, you have dealt with the shear force. You know how to calculate the shear force. Then the third mode of failure of the structure comes the form of bending moment. See, up to this, in your strength of materials, you have determined shear force, bending moment. Then, also, next one is compatibility conditions. See, the beam or any structural element that you have designed may resist to shear force as well as bending moment. But the next things must also be within the safe limits. One is slope. Say for example, the beam is resisting the moment, but it is bent like this. Will you like to sit under this particular beam? Definitely, psychologically, one will not desire to sit under such particular structure. Therefore, whatever slope means, it is that if you draw a tangent at any particular point to the bent shape of the beam, then this particular angle is called slope. So generally it is indicated by theta. So slope must also be within the limit for any particular structure, whether it is a beam, column, or a frame, or a truss. There should not be slope. Means there are certain limits where IS 456 you are using for your RCC elements. So in IS 456 there is a limit for slope. Similarly, the next one is deflection. Deflection means it is the vertical movement of a section. See, earlier beam was straight, and if I take a section here, see, after applying the load, it has occupied this particular position. So, the movement of the section in vertical direction is called deflection. So, this deflection also must be within the limits. These things you are going to follow in case of your all RCC designs. So now, see, load has a relation. See, rate of change of load is called shear force. Rate of change of shear force is called bending moment. This relation already in your strength of materials you have come across. And again, rate of change of bending moment is slow. Rate of change of bending moment is slow. Then rate of change of slope may be called as deflection. They have exact relation with each other. So now I will come to the concept of conjugate beam. Conjugate beam is nothing but a beam which is loaded with its bending moment divided by EI diagram. So bending moment diagram becomes the load for the conjugate beam. See, this is a very important statement one has to remember before we go for analysis of conjugate beams. So, say for example, I will take a simple beam loaded with central load, say some W 100 kilonewton. So now, this is the simple beam. How to make this beam? Let us take this time as 5 meters. See, since load is exactly at the center, the reactions are going to be equal. They are 50 and 50. Right? They are 50 and 50. Now, to draw the bending moment diagram for this particular beam, it is simple beam or normal beam. We can call this as normal beam. So now I will draw the bending moment diagram. Bending moment at the supports is going to be 0. 0 at the supports. And if you take a section at this particular point, 50 into 2, 50 into 2 is, sorry, 2.5 is 135. So 135 kilonewton meters. Suppose they remain the same. Suppose let us keep it same. See now, drawing this is the bending moment diagram for the normal beam. This is the bending moment diagram for the normal beam. I have taken a simple example where a central load is acting on the normal beam. This is the bending moment diagram. 125 you are going to get. See now, in case of conjugate beam method, our object is to determine slope and difference. So I treat this as load. I divide this by EI, right? 125 by EI. This loaded with elastic load. We call it as elastic load because E and I are also. E is nothing but material property and I is nothing but the sectional property, right? So 125 by EI. Now I will treat this particular thing as the load acting on the beam. The bending moment is treated as load. Bending moment is treated as load. So such a beam whose bending moment is treated as load, elastic load, because EI is also considered. That particular beam is called as conjugate beam. So this beam is called as conjugate beam. See, now once you make this conjugate beam, determine the shear force in this. If you want slope at any particular point, I want slope, what is the slope at A? Determine the shear force due to elastic loading. This you must treat it as load. Determine this particular reaction. That reaction becomes the slope at A. Right? So I will call this reaction as RA for the conjugate beam and this reaction as RB. So now, taking moment above this point, equate, okay, shear force let us calculate. Again, because of symmetrical load, triangular load is a symmetrical load. Again, RA is equal to RP. See, now I am going to find the shear force in conjugate beam. So, here, in case of conjugate beam, if I find the shear force at any particular section of the beam, it is called slope at that particular point. And if I find the bending moment at any particular point or any section, that is called the deflection. See now, I will come to the problem. Let us solve this particular problem clearly. Okay. So now I can say slope at A, slope at A is equal to shear force at A in conjugate B. In conjugate B, shear force at A in conjugate B. What is the shear force at A? It is equal to RA equals to, how do you find triangular load? It is nothing but a triangular load. Area of this triangle will give you the complete load. Half into base into height divided by 2, because this load is shared by two supports, one at A and another at B. So I said half into half of this area, triangular area, half into base, that is 5 meter into height, 125 by EI. 125 by EI. Right. See, now I get the slope at A as equal to 1.25 into, okay, I'll keep it as it is because you can calculate. So, 2, okay. 5 into 125. You don't have calculator, so you can calculate yourself, divided by 4 EI. Okay, see, the concept, what we need to understand is what is a conjugate beam, what is the use of conjugate beam, how it is helpful for you to analyze different structures. So, see, now I have determined slope at A. I want bending moment, okay, slope at the center. See, normally what is the slope at the center? The bent up shape is like this, from A to B. Bent shape is A to B. So if you draw a tangent at the center, slope is equal to 0, because this line and the horizontal line, they are same. But slope at A is, this is this one, this angle is theta, I determine. And slope at B is also equal to same angle, that is theta, because of symmetry. Right, now I determine slope. See, we will check whether we get slope at the center as 0 or not. Right, we will check whether slope at the center is 0 or not. Consider left of the section, left part of the section. Triangular load is acting vertically in downward direction and reaction is acting in upward direction. So now this reaction is nothing but half of the load. Therefore, if you subtract this load and this load, you are going to get the slope at the center as equal to 0. So now RA value I have 5 into 125 by 4 EI. Okay, prove it. One or two cases. Slope at center. Slope at, I call this point as C, center, is equal to shear force at C. Shear force at C. So, shear force at C is equal to RA, take it as positive, and triangular load to the left, you take it as negative, because it is acting in downward direction. So now I get slope at C is equal to shear force at C, which is equal to 5 into 125 divided by 4 EI minus this load, this part of the load, this part of the load. So what will be that? Again, it is half into base into height. So half into base is 2.5 meter, half into base into height 125 by EI. 125 by EI. So now you check it. Take your calculator and subtract this one from here, or we can write this as 2.5, because see, okay, divide this by both sides by 2, you get 2.5. Also divide 4 by 2, you get 2 into 125 by EI minus, see, 2.5 by 2 into 125 by EI. So these two are going to get cancelled and slope at the center is equal to 0. See, from this what you should understand, from this particular example, you need to determine the shear force at any section in the beam, conjugate beam. What is conjugate beam? It is the beam. It is the beam loaded with its bending moment and elastic properties. That is M by EI. This is also called as M by EI diagram. See, now I determine slope at A and the slope at C and also slope at B. We will go for the next concept is we need to determine the deflection at A, deflection at the center. See, deflection at A is nothing but bending moment at A, bending moment at A, right? So, if I want deflection, the relation for this conjugate beam is deflection at A is equal to bending moment at A in conjugate beam. See, once again, check the relation. This is what you need to remember before we go into the flexibility matrix, because this basic concept is being adopted in matrix method of analysis in flexibility method. So now, if I want to find deflection at A, will this end deflect? See, free end of the beam is not going to displace. It cannot move up or down. Therefore, deflection must be equal to 0. Let us check whether we get 0 or not. So, I take a section here, consider right part of the section and find the bending moment. So, bending moment is equal to RB into distance 5 meter. Right? Distance 5 meter minus, this is positive bending moment, this gives anti-clockwise, this total load, and CV of this triangle is exactly at the center. So, half area of triangle, half into base into height 125 by EI. This is area of the triangle, that is load, multiplied by center of gravity of the load from point A, because we are taking movement about A, into 2.5. So now, substitute the value of RB in this case. It is 5 into 125 by 4 EI minus 5 into 125 by okay. One of you can calculate this. It will become 5. Multiply this. Here we introduce this one 2 by 2. Multiply and divide. So 2.5 into 2 will give you 5. Okay. Okay. 5 into 125. 5 into 125 by 4A. So, if you multiply this, you are going to get 5 into 125 by 4EI. So, they get cancelled. And the bending moment at A gives you that the deflection at A is equal to 0. But based on the boundary conditions, we already know that the slope is 0. Sorry, deflection is 0. Where the deflection is going to be maximum at the center, because see, the bent up shape of the beam will be like this. Deflection is going to be maximum. So we say deflection at center, is equal to bending moment at C. Bending moment at C. Now consider a section here, right? It is equal to RA into 2.5. That is 5 into 125 into by 4EI into 2.5 minus, see, you are taking section here. One load, it gives positive bending moment, sagging. This load, triangular load, gives hugging bending moment. Therefore, minus half into base 2.5 into height 125 by EI into distance, where it lies. Your section is here, 1/3 of 2.5. 1/3 of 2.5. So, if you simplify this, you are going to get the deflection, maximum deflection at the center. Similarly, RB also you can calculate and check, you are going to get 0 deflection. Because at the support, the beam is not going to yield. That is, the deflection is going to be 0. So now, see, I have solved one conjugate beam. Similarly, while developing the flexibility matrix, one has to adopt this particular method. Okay, we will take one more case. A beam carrying UDL. So I consider a simply supported beam carrying uniformly distributed load over the entire area. Let us say 10 kilonewton per meter. Again, I'll take this as 5 meter. See, now this is normal beam. You need to draw the conjugate beam. Draw the bending moment diagram. How the bending moment varies for UDL? It will be WL square by 8 at the center. So this coordinate is equal to WL square by 8. WL square by 8. W is 10 into 5 square divided by 8. So, you get 250 by 8. So, 250 divided by 8. So, convert this as a conjugate beam. Give two supports, and this load is nothing but 250 divided by 8 EI. 250 divided by 8 EI. And this acts as load. See, now I want to find slope at the support. Slope at the support for this particular beam which is carrying parabolic load. See, this is a parabola. 250 maximum coordinate 250 by 8 EI. Now, if I want slope at A, slope at A is equal to shear force at A in conjugate B. So, what is shear force at A in conjugate B? Shear force at A is RA dash, this RA. Shear force at B is RB. See, because of symmetrical loading, again area of parabola divided by 2 will give you RA and RB. So, I will take half of this area. That is, area of the paraboloid is 2/3 of base into height. 2/3 of base 5 meter into height 250 by 8 EI. 250 by 8 EI. So now you can simplify and we can express the slope at A. Similarly, slope at B is equal to RB. Because of symmetry, RA is equal to RB. And if you want deflection at the center, see, I will take deflection. What is the relation between deflection and conjugate beam? See, the bending moment in conjugate beam at any section is equal to the deflection in the normal beam. This is the normal beam. So deflection is going to be maximum at the center. Therefore, I can say deflection at C center is equal to bending moment at C in conjugate beam. See, this relation you should remember. Slope is equal to shear force in conjugate beam. Deflection is equal to bending moment in the conjugate beam. So now if I take this one, of course I require CP of this road, this particular road. So I can get the deflection by now this particular distance, CG. So now bending moment is nothing but equal to RA into 2.5 positive. It gives having second bending moment minus this load, half of minus load is half of 2/3 of base into height. Base is 2.5 into height, that is 250 by EI into centroidal distance of this. So that centroidal distance normally it will be 1/3 of base. 1/3 of base. Base is 2.5. So now, if I simplify this, substituting the value of RA, then I am going to get the deflection at C. See, why I revised these two problems is, you need to remember one thing. I could not calculate the entire completely, but you can calculate this one. See, it is a revision for you, and you can go to Module 30 or any other book for referring this conjugate beam method. Of course, if you remember only two things, so that will be sufficient. What is conjugate beam? It is a beam loaded with a bending moment with elastic properties E and I. That particular beam, we call it as bending conjugate beam. Why we are making this conjugate beam? To find the slope and deflection. So, what is the relation? Shear force at any particular section in conjugate beam is equal to the slope at that particular section in normal beam. And bending moment at any section bending moment at any section in the conjugate beam is equal to the deflection at that particular section in the normal beam. So, these two things you must remember before we go into the problems analysis by means of using flexibility matrix. Particularly for beams, we are using this particular method, and for frames, we will be using unit load method, and similarly, we are also using unit load method to analyze the trusses. So, before I go into the matrix method of analysis, you must have some of the things. Today I sent you the notes. Please get that notes xeroxed. Get that notes xeroxed and keep it by the side of you. Right? Because in your mobile, the visibility may not be there. I will be doing everything on the board. Right? So I will be solving the problems on the board. Normally, only one problem can be solved in 1 hour because a lot of calculations are involved. You must have my notes adjacent to you. That is one thing. Then, secondly, you must have your calculators. You must sit along with your calculator. Wherever calculation comes, you need to calculate. And try to interact with me. Whenever you get doubt, please contact me so that I can clarify your doubts. So from Monday onwards, since I have already completed 5 modules, almost 5 modules are over in construction management. Therefore, those classes also in next week onwards, I will be utilizing to teach you the matrix method of analysis. Of course, if you understand the concept, definitely it is a very easy chapter, and drawing the bending moment diagram and all same as that of your Cornish method or moment distribution method or slope deflection method. So, the essential requirements that you should have before attending the class is my notes. Get my notes xerox, keep it adjacent to you, have a calculator, and you need to actively participate in calculating the things. So, for starting the beams from Monday, I require this concept because to develop the matrix, I am invariably using this particular method. And some of the formulas I will do the writing on the board. You please just copy down because say some of the things, very basic things you should remember. That is. What is the bending moment under UDL? It is a parabolic curve with maximum ordinate WL square by A. Then similarly, if a beam is given, low is eccentric. If you say AB, what is the maximum bending moment? In this case, the maximum bending moment occurs under the load. And what will be its ordinate? See, these things are very basic things from your strength of materials. WAB by L. WAB by L. Right. So, some of the very basic things you just need to remember and apply in determining the flexibility matrix. So, today, I hope you have understood. What you need to remember is what is a conjugate beam. Conjugate beam is a beam which is loaded with its bending moment and elastic properties. So it becomes conjugate beam. Shear force at any section in conjugate beam is equal to the slope at that particular section in the normal beam. This is first thing. Second thing is bending moment at any section in the conjugate beam is equal to the deflection at that particular section in the normal beam. So, with these relations, definitely we can go into this particular matrix method of analysis. So from